All right, welcome to this explainer. Today, we are launching a sharp, investigative look into a massive, glaring flaw in modern technology. We're going to expose the illusion that standard AI actually understands the world it operates in. Because right now, what we loosely call artificial intelligence is really just advanced pattern matching. And as you're going to see, that creates a profoundly dangerous blind spot.
So let's dive right into this with a killer example that perfectly illustrates this misunderstanding. Think about standard image recognition. What actually happens when a machine learning model, one that's been trained on thousands of normal pictures of cows in grassy pastures, suddenly sees a picture of a cow standing on a sandy beach?
Well, it fails. Actually, it fails catastrophically. The model looks at the beach and says, nope, there is no cow there. Why? Because standard deep learning is, at its core, just a lazy curve fitter. It minimizes a loss function by finding literally any statistical shortcut it can. So instead of learning what a cow actually is, the model just learned that a bunch of green pixels, the grass, causes the classification cow.
But a causal model completely corrects this fundamental misunderstanding. It succeeds because it actively identifies invariant mechanisms. We're talking about the physical shape, the snout, the ears. It completely ignores the green grass because the background is entirely irrelevant to the true unchanging nature of the animal. And this brilliantly highlights our core thesis today. Mere statistical correlation is absolutely never enough.
So, here is our roadmap for today. We'll start with the fundamental AI illusion. Then, we'll look at spurious correlations, followed by entering the causal world, graph surgery teaching AI to intervene, and finally, the future of robust AI.
Let's jump straight into part 1, the fundamental AI illusion. You see, in that cow example, the AI fell victim to what is known as a spurious correlation. It's a false connection. Two variables move together statistically, sure, but one absolutely does not cause the other. Relying on these false statistical shortcuts is exactly why standard models just hit a brick wall. When the environment changes, like when the cow steps off the grass and onto the sand, the statistical illusion shatters.
Okay, moving on to section 2, spurious correlations and confounders.
Consider this classic, almost terrifying scenario. Imagine a statistician observing some city data, and they notice a trend. Whenever ice cream sales go up, the number of drownings goes up too. If an AI merely calculates the standard probability, it might confidently and falsely assume eating ice cream causes drowning. It completely misses the underlying reality. It misses the temperature, which is the true hidden confounder here. The rising summer heat causes both the ice cream sales to spike and more people to go swimming, which sadly leads to more drownings.
And that brings us to section 3, entering the causal world.
This perfectly illustrates a stark pipeline reality. Standard ML is the statistician, a passive observer just calculating the probability of Y given that we happen to see X. But causal ML? Causal ML is the engineer. The engineer calculates the probability of Y given that we do X. The statistician is just passively watching correlations, while the causal engineer steps in with a scalpel to ask, wait, what happens if we actively intervene? Like if we just ban ice cream, intervening on X, will drownings miraculously stop? The causal engineer knows the answer is no, because the temperature, the root cause, hasn't changed.
Let's look at how we actually do this in section 4, graph surgery and the do operator. We start by building a structural model from scratch, a directed acyclic graph, or DAG. Imagine drawing the nodes, your confounder Z, your input X, and your outcome Y. Now draw the causal arrows representing the actual physical mechanisms. Z causes X, Z causes Y, and X causes Y. When you trace this backwards, you find a path flowing from X up to Z and then down to Y. That is a spurious backdoor path. It is quite literally a non-causal pipe leaking false statistical correlation directly into our data.
Now enter AI pioneer Judea Pearl's do operator. This is where it gets really cool. When we intervene, when we physically force X to be a specific value, like officially banning ice cream or assigning a drug to a patient, watch what happens. That arrow from Z to X visually dissolves into mist. It just vanishes. By intervening, we sever X's dependence on its natural causes. X becomes an orphan node. We have physically cut that spurious backdoor path, entirely stopping that leak of false correlation. It turns abstract logic into a literal, visual act of surgery.
But look, here's the real challenge. We can't always run physical experiments or massive randomized controlled trials, right? We can't actually ban ice cream everywhere just to test the theory. So we use the backdoor adjustment formula. Since we often only have observational data, this formula acts as our mathematical scalpel. By iterating over every possible state of the confounders, those z variables, and reweighting the data by their natural distributions, we mathematically choke the spurious path. We are simulating that physical graph surgery without ever having to run a real-world experiment.
Which leads us to Section 5, Teaching AI to Intervene. So how do we actually inject this causality directly into deep learning architectures? Engineers use techniques like invariant risk minimization, or IRM. Instead of just lazily minimizing errors to get the highest accuracy on a training set, IRM adds a really strict mathematical penalty. It forces the neural network's weights to be penalized if it features predictive power shifts across different environments. So if that green grass shortcut works perfectly in a pasture, but fails miserably on a sandy beach, the penalty is massive. The network is essentially mathematically tortured until it finally drops that environment-dependent shortcut, forcing it to focus solely on the cow's true invariant shape.
Finally, let's wrap up with Section 6, the future of robust AI. AI researcher Judea designed the famous ladder of causation, and it shows us that standard machine learning today is mostly just stuck on level 1, association. It's nothing more than a passive observer seeing what happens to occur together. Level 2 is intervention, using that do operator we just talked about. But true intelligence, level 3, that requires climbing even higher. It requires counterfactuals. It requires individual-level causal models to truly understand the world.
So, I want to leave you with this provocative thought as we close out this explainer. As engineers rebuild these systems from the ground up with causal graphs, injecting the do operator and invariant risk penalties right into the architecture, what will it actually take for AI to cross that final threshold? When will our models stop just passively observing and finally be capable of true counterfactual reasoning, asking what would have happened if I had acted differently? Because make no mistake, that is the ultimate, final frontier of artificial intelligence.